Good afternoon and welcome once again to our lectures on inorganic chemistry. Today we want to discuss the coordination chemistry like I said in our last lecture. I'll take the introductory part of coordination chemistry and we continue it in our subsequent lectures. Before discussing coordination chemistry, it is worthy that we make a remarkable difference between the type of bonds we have in chemistry. Coordination chemistry is marked by the type of bond that the compounds that fall within the coordination chemistry forms. We start by looking at what is a chemical bond. A chemical bond may not be easy to define, but for the purposes of this lecture, we would say that a chemical bond is the resultant force of attraction holding two or more atoms together after such atoms have interacted with one another through their valence electrons. That is to say, before a chemical bond is formed, there must be electron-electron interaction, and the readily available electron to interact are the outermost electrons, which we call the valence electron. From the definition above, we may say that all the reacting atoms must not donate or contribute electron or electrons, but at least one must give an electron to the other to allow for a drop in energy, therefore bringing an attraction between them. By saying so, one can now say that a chemical bond is a force holding two or more atoms that have chemically combined together. When we say chemically combined together, we mean they have interacted at the electron level. Either somebody has given an electron, somebody has taken an electron, or somebody has brought an electron for the other to share. Before we continue, please, on this slide, you have the link that will lead you to the PDF version of this lecture. We go ahead and look at the ionic or electrovalent bond. This is that bond that is formed between the metal and the non-metal. When you say the metal and the non-metal, you mean elements to the far right and elements to the far left. Elements to the far left, my left in this regard, are the members of group 1 and 2. And when you say members of group 1 and 2, you mean those elements that have 1 or 2 electrons in their valence orbital. They have the propensity of giving out electrons because they have 1, 2, or 3 as the case may be. And they want to attain octet. And for them to attain octet, they will readily give out their valence electrons to attain the electronic configuration of the nearest noble gas. For this reason, we say they are electropositive. They take in ionization energy, and by it, they send out their valence electron. And before they can send out their valence electron, there must be an electronegative atom ready to accept these electrons that the electropositive will send. The electronegative atom must possess electron affinity, which is the energy it requires to give out for it to be able to accept electron or electrons. When an atom gives out an electron, he forms a cation. When an atom accepts electron, it forms an anion, meaning that when ionization energy is taken in, an electron is given out, the atom that has so given out the electron is no more an atom, it is called an ion, a cation precisely. Conversely, the one that has accepted must give out electron affinity, the energy called electron affinity. By it, there shall be electrostatic force of attraction. And you can see from From our schematic here, energy as in the triangle H, enthalpy H you have seen will come, an ionic bond will be formed, as you can see in the green link between the big anion and the small cation. When an atom gives out an electron, it becomes smaller in size. When an atom accepts electron, it becomes bigger. So at that point, electrostatic force of attraction will come in and an ionic. And we go further to see yet another type of bond called the covalent, from the word co, meaning cooperate, bring together by agreement. This is mostly the bond formed by non-metals. Hydrogen, oxygen, chlorine, and the rest, they will rather share electrons. They will share electron by the combining species, bringing equal number of electrons to share. So in this schematic, you can see that one brings the red and the red or purple, you call it, electron, and they share to form a molecular orbital. At this point, you are talking about a covalent bond, the dative covalent and or the coordinate bond. After having looked at the ionic and the covalent, there is yet another type of chemical bond called the dative covalent or coordinate bond. This is a bond that is formed by two or more chemical species. To be able to form this bond, there shall be two distinct species. One is called a ligand. A ligand or a nucleophile is a chemical species that has lone pair electron. Lone pair electron. That is two electrons together, while the other species must have a vacant orbital where the lone pair electron, one will be sent into it and the other one will be kept by the donor, and they will now form what is called a coordinate bond. By coordinate bond, we mean an atom will come with an empty bag, while the other atom will come with two oranges. And for this atom to share this bag with the owner of the bag, he has to put one orange inside the bag. At that point, the two of them hold the bag. The bond that links the two atoms is the bag they are holding. And that is the bond or the compound we called coordinate compound. As you can see in the schematic, that atom B had two purple electrons, while atom A had a spherical empty orbital there, and from the spherical empty orbital, the atom A is able to send the electron. These electrons are shared, and you call that dative covalent or bond. We go ahead to discuss dative covalent bond or coordinate compound. A dative covalent compound or a coordinate compound is a compound that has a metal center, as you can see in our slide, M, and ligands surrounding it in an orderly geometric form. We call it spatial, S-P-A-T-I-A-L, spatial orientation. It occupies a definite position within the coordination geometry. And there may be more than one kind of bond in a coordinate compound. You may have the coordinate bond and an ionic bond. For this reason, the bond that is formed within the square bracket is or are referred to as coordinate bonds. But the bonds that are formed outside the square bracket are referred to as the ionic bond. You can see the metal center, the ligand, and the anion satisfying the primary valency, while the ligand satisfies the secondary valency. So by definition, we can say a complex or coordination compound can be said to be that chemical species that is formed by the association of two or more simpler species that has been existing and is capable of existing independently. The resultant product of such an association may be a double salt such as dolomite and potash alum having water of crystallization embedded. Apart from existing as double salts, they also exist as complexes. This refers to those chemical species that bear metal center having vacant orbital capable of accepting electron and ligands occupying such vacant orbitals in an organized spatial arrangement or geometry around the metal center, such as coupled I mean the coupled of this compound of ammonia with cobalt, this compound of platinum with chlorine or chloride, and this compound of copper with water. As you can see by the geometry, it is here. Ammonia is surrounding cobalt in its geometry as you can see it here. That is hexaamine cobalt 2. And here you can see water, 4 molecules of water surrounding copper. Same applies. What do we therefore refer to as coordination number? In the view of Alfred Wegener, coordination number is the number of bonds formed between the metal center and the ligand. This can be between 2 and 8 and even more depending on the number of available vacant orbitals, as can be seen in our structure below here. Further on, what are the factors that may affect coordination number? The size of the metal center. If a metal center is large, as is in the case of atoms of element to the far left or atoms of the element to the lower group within the group, they are capable of forming a larger number of coordination sphere. So the higher the space, the bigger the atomic radius of the metal center, the higher the ability. The same applies if the ligand is bulky. A bulky lipid ligand will pose an interference, will not allow other ligands to enter. So these are those factors that may affect. You may please review some other factors that may, but for the purpose of this lesson, these two suffice. Once again, we want to please request you to please visit the net and